Hello, and thanks for tuning in again. It's Johannes again here with Packet Tuesday. Well, I got something special. Last time we talked TLS, and I sort of promised that next one will be the server hello instead of a client hello. Sorry, a small change in plans, but I hope it's worth it. Well, stuff happens, and in this case, a vulnerability happened. And there's nothing better to talk about than a vulnerability that was just made public and deals with sort of little intricate IP features. So I had to latch on to this, and you'll see it's a great vulnerability, something real fun, interesting packets involved, and it involves the ping utility. Yeah, ping. Ping. I don't know. 30, 40 years old, basically as old as the internet. Probably one of the first network tools that you ever used when you sort of started playing with IP was a ping. So how can it possibly have a vulnerability? And that's sort of where we want to dive in to a little bit. Ping, of course, in a sense, ICMP echo requests. Normally, if all goes well, you get an ICMP echo reply back. But sometimes things don't go right. Sometimes a host is not reachable, or maybe you get even duplicate replies back and such. So in that case, you get an ICMP error back. And ping has to parse these ICMP errors, and that's kind of where the problem happens here. So let me just show you a couple of things here. Let's first start with the vulnerability. So let's just switch here to the browser. No, that's not the browser. Okay. Yeah, this is the vulnerability, as you see, released on November 29th. Affects all current versions of FreeBSD. And of course, BSD is sort of the original IP operating system. Pretty much, all IP stacks that we are using these days are sort of derived from BSD. Anyway, and yeah, it deals with these ICMP errors. So first of all, let's take a little bit of a look at what ICMP errors are supposed to look like. And here I have the ICMP header. This is from RFC 792. That's the ICMP RFC. One of those small numbers, one of those original RFCs. And here we have our ICMP header, type and code, where type 3 means that something is unreachable. And then the code tells us what's not reachable. So if it would be a host unreachable, it would be a 1. We'll later look at the port unreachable packet, so 3.3. Next, we do have the checksum, 2 bytes. And then we have 4 unused bytes. For ICMP echo requests and replies, that's, for example, your ICMP ID and ICMP sequence number. But here for error messages, they're not used. And then following that, sort of as payload of the ICMP message, we do have the packet that caused the error. And this is actually important. It's not just for debugging. There's sort of a security issue here. We have to prevent someone spoofing these ICMP error messages. If you think about it, you're trying to send a message, a DNS query, to Google's DNS server 8888. And then all of a sudden you're getting a message back, an ICMP error message, host unreachable. The source IP of that message, if it's legitimate, is the router that finds out that 888 is not reachable. We have no idea what that router would be. So an attacker can use any source IP address to send the message from. So how do we know that this is actually an authenticated, an authorized message? Well, of course, there is no digital signatures here. That's not sort of what IP does. Instead, we are embedding the packet that caused the error, which is a packet that I sent. And then I can check, hey, did I recently send a packet with this IP header? And then you're seeing I'm also supposed to include at least 64 bits or 8 bytes of then the IP payload. So 8 bytes would, for example, just be a UDP header. But often you'll see more included. And now an attacker would have to spoof that entire packet, with IP IDs, port numbers, if it's TCP sequence numbers and things like that. And that makes it difficult, if not impossible, to sort of blindly spoof these ICMP error messages. But anyway, so this is how it works. We send a packet, the packet causes an error, the ICMP error message coming back will include the first few bytes of the packet that caused the error. So knowing that, let's now look at a packet. Okay, and I already have this prepared for in the prior episodes. I always sort of acquired this on camera. I figured, well, I've done it a couple times, so don't have to do this in every single episode here. And this is our error message. So what I did here is I did send a DNS query to a system on my network. The system exists, but it's not actually a DNS server. So I do get, and you already see this up here, that UDP port 53 unreachable back. Okay, let's take the headers apart here. And let me just overlay this here, trying to keep the header diagrams a little bit bigger. I think that sort of works reasonably well. And then, so let me fill in here what's going on. So in TCP dump, we start out here with the IP version and IP header length. So that's 4.5. Then we have our type of service, Charlie 0. It's not 0, we're doing something a little bit different here. Then we have our total datagram length, 0, 0, 5 echo. So that's 5, 0 is 80, echo is 14, so that's 94 is our complete datagram length. And if you look at the length here, 64, that's the IP payload. So this does not include the 20 bytes for the IP header. That's sort of how TCP dump displays that. So 94 bytes for the complete IP packet. Then we got our IP ID, 3636. Funny little number here. Then we got our flags and offset. There's nothing. All 0. So nothing happening here with fragments. Then we got our TTL 3 Foxtrot, 3F. So this is here our TTL. It's probably start out at 4.0. That would be a standard TTL for Unix, 64. But notice how it comes from 10.5.3 and going to 10.5.1. So this is going between different subnets. So we lost one TTL here at that router. Then our protocol, of course, is 1. It's ICMP. Then we have our checksum, 2 Charlie 03. No reason to believe that this is wrong. Then we have our source IP. So that's 0 alpha, so 10, 05, 5, then 3, 03, and then 1 Foxtrot, and that would be 31. And then I have 10, 5, 1, 7 echo. Yeah, and that's 10, 5, 1, 1, 2, 6. So, okay, this is our IP header. So let's just mark this here. So this is where our IP header ends and our ICMP header starts. And now remember the ICMP header. We have our type and code 33, port unreachable. And that was the ICMP header. And then we have our checksum 15 echo 3. Then we have those 4 bytes of unused data. These are these 8 zeros here. Yeah? 1 byte being 2 digits. So this is now the end of our ICMP header. And then notice how it continues with a 4-5. 4-5 being sort of the typical start of our IP header. And so now let's just put this cheat sheet. I should have used a cheat sheet for the second IP header. But 4.5 IP version 4, header length 20 bytes. Type of service 0. Then we have our total datagram length. 4.2, so 64 plus 2, so 66 is the complete length of our packet. And that was the original length. Yeah, so this is not necessarily what's embedded here, but this was the original length of the packet. And remember, we may not have, I think here we actually have the entire packet embedded, but we may not, it may be cut off at some point. Okay. So this was here our total length. Then we have our, just get this here, our IP ID, Sir Charlie 22, and this was the original IP ID again of the packet. Our flags and offset 0, 3 Foxtrot for our TTL, which makes sense, yeah, because it probably also lost 1 TTL on the way there. Now our protocol is 11 or 17, which means it's UDP. Then we have our checksum, our IP address, 10.5.1.7 echo. You see that's the source IP is now our destination IP. And then our destination IP, 10.5.3.1 Foxtrot, is, well, where the error came from. Port unreachable typically comes from the system that I'm trying to send the packet to. So here we don't sort of have that ambiguity where it may come from a random router. Okay. So this is then where our second IP header ends. So this was let me use a different color here. Let me do this nice and neat. Oops. Well, as neat as I can. So what I have underlined in green here is the IP header of the packet that caused the error. And this is the ICMP payload of that error message. So following that IP header, given that we have UDP, we now have a UDP header. Let me switch colors here. So our UDP header starts here with the source port, some high port, destination port, 35 or 53 in decimal, so DNS. So that's what we expect. I told you I'd send a DNS packet. Then our UDP length to echo. And actually, I do have a diagram for that. So this is now our UDP length. 0, 0 to echo, so 32 plus 14, 46 would be the complete UDP length here. And then we do have our UDP checksum. And that concludes the UDP header here. Now, since port 53, we do have a DNS header next. So let's pull up the DNS header diagram here. DNS header starts with the query ID, 385 Charlie. Then our flags, we again sort of have our recursion desired flag set here. Then we have the number of queries. There's 1 query here. It's a query, so there's no answer. There are no authority records. And then there is an option, and it's exactly what we talked about, like, I think it was 2 episodes ago, when I talked about eDNS 0. So if you haven't watched that video yet, that's where we talk about this particular option that you're seeing here. And then we have our query, so 5. We can cheat here a little bit. Yahoo, then 3, com, 0 here then concludes the hosting we're looking for, and we're looking for type 1, the A record in the internet class. So a DNS query for the IPv4 address for yahoo.com. And then, like I said, the option that's following here, that's the 29 and 100. We'll talk about that later, like I said. So that's, but anyway, that's a normal error. Now, let me just show you the packet that caused the error here. And you see here 45042 Charlie 22 0450042 Charlie 22. And so that's the packet here. And like I said, we have actually the entire packet included here, not just IP header and the next 8 bytes. Okay, so like I said, everything normal so far. So what's the problem here with ping? Let's go back to ping here. Okay. Let's read a little bit more this advisory here. Okay. And turn off the scribbles. So ping reads the IP packet from a network to process the response, which is fine. There is this prpack function. And it needs to parse the ICMP header of the quoted packet. And that created the error. And the problem now is, but if the packet that's included, this quoted packet, the packet that caused the error, if that packet contains IP options. So, okay, what's the problem here with IP options? Well, let me switch to my whiteboard here. Well, the options here are at the end. So usually IP headers are 20 bytes. And we have here that IP header length 5 times 4, 20 bytes. 99.99%, and if you would have asked me like a few weeks ago, I would have told you 100% of packets on your network are using an IP header with 20 bytes. But there is this variable header length. So it could be something else than 5. And it is something that's not 5 if we have options. So this is kind of what's happening here. Let's look at the source code here for ping and see what's going on here. And I pulled this up here. This is the ping source code. And then there was this prpack function. Let me try and find that. Yep, here it is. And then the problem here is we are copying this buffer. We are using the header length. You see here how we actually pull out the header length. And we copy that many bytes, basically the header length number of bytes, into this IP structure. And that IP structure, well, is just structure IP. We have it defined here. That's this IP structure. It's header length, version, type of service, length, IP ID, offset, so our fragment fields. Then we have our TTL, we have our protocol, checksum, and our IP addresses. It's the entire IP header without options. So the options are not taken care of here. Instead, what happens is, basically this structure here is always 20 bytes. So what I'm doing here with ping is, I'm copying the entire header length which may be larger than 20 bytes if it has options, into a structure that's only 20 bytes. Well, and then you have your classic buffer overflow happening here. So, okay, easy enough. How do we find someone exploiting this? Well, we basically have to look for ICMP error messages where the embedded IP header is larger than 20 bytes. And we know it's larger than 20 bytes. If I go back here, if this byte here is not 45, if this is larger than 45, and this is always in that same location. So it's always the first byte of our IP, of our ICMP payload. So it would be easy to write a snort rule or something like this. Hey, if that first packet is not 45, then we have a problem here. And no issues here with IPv6 because we are looking here at ICMPv4, which only works with IPv4. So we don't have to worry about IPv6. We have ICMPv6 for IPv6. So, okay. So that's kind of what we could do. Now, the other problem that we have is, well, are there normal packets on your network that have IP options? Like I told you, IP options are hardly ever used. But there are some cases where you have legitimate IP options in packets. And if you want to know more about this, well, you have to come back in 2 weeks. Because next week, I'm hopefully going to do the TLS server hello. Maybe I'll do this one first. But there is a certain, not that uncommon case where you will see IP options in your local network. And that's what I want to talk next. It also involves multicast and such. So not to give you away too many spoilers here. Too much to put it all in this video. So I'll make that another video. Thanks for listening. Thanks for watching. Please subscribe. Please tell your friends about it. This is exciting stuff. So I hope you enjoy it, and stick around for the next episode in a week, and then we'll talk about, hopefully, like I said, the server hello, and then maybe IP options. Maybe I do it the other way around. Whatever works. Thanks, and talk to you next Tuesday. Bye.